So now for the exciting conclusion of the dimension of a sum theorem. Let's see where we were. So we had that there was a basis u1 through um of the intersection, and then we had u1 through um, and then v1 up through vj would give us a basis of u1. u1 up through um combined with w1 up through wk would give us a basis for u2. And now we're looking at the list that has all of the u's and v's and w's, and we claim that this is a basis for the sum space. Okay, and that's what we have to do now, prove that claim. So let's get some space going on and go for it. So proof of claim. All right then. So first off, we'll look at the proof that L spans the sum. Okay. So for this, we know that L contains a basis for U1, namely just the U's and the V's parts of it, right? So we know that the, whoops, wrong way around. So we know that U1 is contained in the span of L. And then similarly, or BSA or whatever, we know that U2 is contained in the span of L. So then we know that the sum is contained in the span of L as well. By definition of the sum of two vector spaces. And then we have the other direction. So the reverse containment. But this is immediate. Right? So the span of L is contained in U1 plus U2, again because of the definition of span. Okay. And I guess also because every element of L is in, so let's just say every U in L, so every element of the list is definitely in U1 plus U2. Okay, so that does it for span. So that was the first part. But then for something to be a basis, we also have to have that it's independent. So suppose that L, so suppose we have a dependence relation. So now this is going to be a long hairy mess because of all the parts involved, right? So we've got A1, U1, so a linear combination of the U's and a linear combination of the V's and a linear combination of the W's. Okay, so we've got all of this stuff, linear combination of all these guys adding up to 0. So so that's a dependence. Okay, so a dependence or a dependence relation, whatever. Okay, so then let's look at these parts here, right? So what do we have? So we've got that. So this part here, this is a component that lives in U1 intersect U2, and then we have a component right here that lives in. And actually, you know what? Let's give these names just to make life easy. So the thing made out of u's, I'm just going to call u. And then this thing made out of all the v's, I'm going to call it v. And so it's an element of u1. And then this thing that's made out of w's here, this I'm going to call it w, and it is an element of u2. Okay, so now what I'm going to do is rewrite w a couple different ways. It's amazing how much can be accomplished in mathematics just by rewriting something a different way. So if in doubt, push the symbols around on the paper for a little while. Maybe we'll get lucky. So rewrite w as minus u minus v, right? Just subtract the u and the v over to the other side. And then when you look at these, what do you have? Well, you know that u is in the intersection of u1 and u2. So in particular, it's an element of u1. And v is also an element of u1. So that tells you that the difference of them is also going to, or the negative of the sum of them is also going to be an element of u1. Okay, well, then that puts w in u1 intersect u2, right? Because we started off with it being in u2 just from the get-go, right? And then since it's also in u1, then it must be in the intersection. Okay, so we have a basis for the intersection. So we can rewrite w again in terms of that basis. So it would be, now the basis for the intersection is the one consisting of u's, and we run out of coefficients, so let's call it d1 u1 plus blah blah up to dm um. Okay. So then let's see. So now if I expand what I've got on the left-hand side there, that w, if you remember, was c1 w1 up to ck wk back in the beginning, and now we've shown that it's equal to this other thing. What does it go up to? D's go up to m. There we go. Okay. But the u's and the w's form a basis for u2. So this is a dependence relation in the basis of u2. And since bases are linearly independent, the only way you can have a dependence relation is if all the coefficients are 0. So all coefficients vanish. So we have c1 equals up through ck equals d1 up through dm, all equal to 0. Okay, now look at what that means back in this equation here. So if I rewrite that equation, now I have a1, whoops, a little off target there, a1 u1 plus up through am um, b1 v1 up through bj vj, and then all the c's are equal to 0, and that's equal to 0. So now this guy, maybe let me move that over a little bit. Okay, so now this guy here is a dependence and a basis of u1. So all these coefficients vanish as well. So all the AIs and BJs and whatever are all equal to 0. And then that tells us that in the initial dependence in L, all coefficients have to be equal to 0. And so we are done.